All right, again, that's for section 9.4, which deals with improper integrals. So this have infinite limits of integration. So we've got a couple examples. F of x is continuous on the interval a to infinity. Then you can essentially replace your infinity with let this value approach infinity. Same thing if it's a negative infinity up to b, or if it's infinity to positive, or negative infinity to positive infinity, you just split it at some number c and call it good. So example 1, express the improper integral negative infinity to positive infinity of e to the x dx in terms of the limits of definite integrals. So what we're going to do is the first thing we're going to do is we're going to break it into two integrals at some number. Doesn't really matter which one you use, so pick a nice one like 0. And we're going to turn this into limit. So the limit, as we'll say, a approaches negative infinity of a to 0 via the x dx, plus limit as b approaches positive infinity from 0 to b via the x dx. Okay, so now we need to evaluate. Well, the antiderivative of e to the x is just e to the x evaluated from a to 0 plus e to the x evaluated from 0 to b. So this is going to be the limit as a approaches negative infinity of e to the 0th minus e to the 8th plus limit as b approaches infinity of e to the b minus e to the 0. This is always upper bound minus lower bound. So this is going to be 1 minus e to the negative infinity plus e to the infinity minus 1. Okay, so this is actually 0, so this becomes 1 plus e to the infinity minus 1. Oh, sorry, this becomes 0. No, I was right. Oh, I'm messing this all up. This is essentially 1, because that becomes 0. This whole part eventually becomes infinity. So you can't actually evaluate this. This thing has an infinite area. All right, example 2, this is improper integral 1 to infinity of dx over x converge or diverge. Now this is the same thing as 1 to infinity of 1 over x dx, if it helps you think about it that way. So we're going to do this. The limit is b approaches infinity of 1 to b of 1 over x dx. So the antiderivative of 1 over x is the natural log of x evaluated from 1 to b. So that's the limit as b approaches infinity of the natural log of b minus the natural log of 1. Well, the natural log of infinity is infinity. The natural log of 1 is 0. So this diverges. You do not get a numerical answer. The area grows forever. All right, evaluate this guy, state if it diverges. Okay. So we're going to have to use partial fraction decomposition for this guy. So we've got the limit as b approaches infinity from 0 to b of 2 x squared plus 4x plus 3 dx. So to do partial fraction decomposition, we're going to say 2 over x squared plus 4x plus 3 is equal to something over, so you need to factor this denominator, so it's going to factor as x plus 1 and x plus 3. So multiply by this, so 2 equals a times x plus 3 plus b times x plus 1. So when x is equal to negative 3, I get 2 equals negative 2b, so b is negative 1. When x is equal to negative 1, I get 2 equals 2a, so a is 1. So this decomposes as, let's see here, the limit as b approaches infinity from 0 to b of 1 over x plus 1 dx plus the limit as b approaches infinity of negative 1 over x plus 3 dx. Okay, so then we got to evaluate. So this is going to be the limit as b approaches infinity of the natural log of x plus 1 from 0 to b plus the limit as b approaches infinity of the negative natural log of x plus 3 from 0 to b. So this is the natural log of infinity plus, minus the natural log of 1. So plug b in, and b is infinity. Plus, over here, negative ln infinity. Plus, this is going to be a double negative, ln 3. Okay. So, let's see here. So ln infinity, these guys cancel. ln 1 is 0. So the whole answer is just the natural log of 3. So this converges. Evaluate this guy, or state that it diverges. So the limit as b approaches infinity from 1 to b of x e to the negative x dx. So we need to do this with integration by parts. So we need to define our u's and our v's. So u is going to be x, so that du is 1. dv is e to the negative x dx, which means v is negative e to the negative x. So let's see here. It's u times v. So negative x e to the negative x from 1 to b minus the antiderivative of v du, which is just negative e to the negative x dx. So we can rewrite them from 1 to b. So negative x e to the negative x from 1 to b plus the antiderivative of, 1 to b of e to the negative x dx. And we still have all this limit out front here. So negative x e to the negative x from 1 to b plus negative e to the negative x from 1 to b. So since we have the same bounds, we can combine these. So negative x e to the negative x minus e to the negative x from 1 to b. So we can factor out a negative e to the negative x. This gives me x plus 1 from 1 to b. We still have the limit as b approaches infinity all the way up front here. Okay, so let's see here. So this is going to be negative e to the negative b times b plus 1 plus e to the negative 1 times 1 plus 1. So it becomes plus because it would be a double negative. But b is infinity, which means this becomes e to the negative infinity, which is 1 over e infinity. So this whole thing goes away, which just gives us 2 over e. This is 2, that e goes to the bottom because that's a negative exponent. Okie dokie. 5, evaluate this guy. All right. So first we're going to break it. So the limit as a approaches negative infinity from a to 0 of 1 over 1 plus x squared dx plus the limit as b approaches positive infinity from 0 to b of 1 over 1 plus x squared dx. So break it at any number you want, doesn't really matter. So let's see here. The antiderivative here is the inverse tangent. So the limit as a approaches negative infinity of the inverse tangent of x from a to 0 plus the limit as b approaches infinity of the inverse tangent of x from 0 to b. So the limit as a approaches infinity of the inverse tangent of 0 minus the inverse tangent of a plus the limit as b approaches infinity, inverse tangent of b minus the inverse tangent of 0. So the inverse tangent of 0 just becomes 0. The inverse tangent of infinity is pi over 2. So minus pi over 2. Nope, negative infinity, so plus pi over 2. So this whole thing is just pi over 2. Over here, the inverse tangent of infinity, that's positive pi over 2, plus 0. So all that is just pi over 2. So pi over 2 plus pi over 2, the limit is just pi. So even though our bounds go on forever, there's a finite area underneath. All right, you can also have integrands with discontinuities, which means the graph has a spike or something. Integrands of functions that become infinite at a point where the interval integration are improper integrals. So f of x is continuous from a to b. You essentially let you approach from the left or from the right. So here, where c is you can break it apart as c and then combine the two together. All right, so 4, 6, 0 to 3 of this guy. So the issue is we have a discontinuity at x equals 1, because if we try to plug 1 in here, it can't work. So we have to break the graph at 1, essentially. So we treat it like this, from 0 to 1, of 1 over x minus 1 to the 2/3 dx, plus 1, 2, 3. So it looked like this. So let's see here. This guy is going to be x minus 1 to the 1/3 if I count the exponent up. So I'm going to need a 3 out front to balance it out. So from 0 to 1 plus similar thing's going to happen here. 3 quantity x minus 1 to the 1/3 from 1 to 3. So this is going to be, if I plug 1 in, I get 3 times 0 to the 1/3. If I plug, so that's this one. If I plug 2 to the 1/3 minus 3 times 0 to the 1/3. So these guys go away. So this is just 3 plus 3 cube root 2. So there's your answer. But we have to break it at 1, because otherwise it's not a value. You can't evaluate it through there. You have to separate it. Okay, example 7. Evaluate this way from 1 to 2. So this has discontinuity at 2. So what we're going to do is, let's see here. So this is the same thing as from 1 to 2 of 1 over x minus 2 dx. So this is a natural log from 1 to 2. So if we try this is the natural log of 0 minus the natural log of -1. Sorry, forgot the absolute value bars. So ln 0 minus ln 1. Well, ln 0 is negative infinity, ln 1 is 0. So this whole thing is negative infinity. So you have a negative infinite area. Diverges, has no value. Okay, test for convergences and divergences. So the comparison test, let f and g, that should be b, continuous on some interval a to infinity, with 0 is less than f of x less than g of x, so g of x is always more than f of x for all x greater than some number a. From a to infinity, f of x of dx converges if g of x converges, because if g of x converges, it has to level off, and if g of x is always more than f of x must then also level off. G of x diverges if f of x diverges. So since f of x is the lower one, if it grows forever, that forces g to also grow forever. All right, so example 8, the integral 1 to infinity of e to the negative x squared dx, converge or diverge. So let's see here. So we can do the limit as b approaches infinity from 1 to infinity of, well, that's a terrible infinity sign. There we go. E to the negative x squared. Okay. So we can't really do this exactly, but we know that this thing is always less than or equal to this. Because if this exponent is bigger, it forces the whole thing to be smaller. So if this one converges, then this one's forced to converge as well. So we need to see if this guy has a limit, or we can do it. So this becomes e to the negative x from 1 to infinity. So negative e to the negative infinity plus e to the negative 1. Well, this is 0 plus 1 over e. So this has a value, which means that since this one must be less than it, it must also have a value. Now, we don't necessarily know what it converges to, we just know that it happens to converge. Oh, use a calculator to estimate its value. Okay. So, option, calc. So we got e to the negative x squared from 1 to, so the calculator can't do infinity, so we need to pick just like a relatively large number. So, I typed that in wrong. Oh, whoops, yeah. Can't do that. Calc. There we go. So I'm graphing the integral itself to see if it levels off. So okay, so if we trace, we can read these y values. So it looks like it's about 1.39 or 0.139. Can't really see. There we go. Oh, almost got it. There we go. So if we trace out, we get 0.1394. So I graphed the integral. I graphed that equation, except you put x there to make x get bigger and bigger and bigger. Okay, number 9. Let's be capital U. Use the arc length formula from section 8.4 to show the circumference of a circle, blah, 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 is pi. Okay, so what we're actually going to do is we're going to only worry about part of the graph. So what we can do is do, let's see here, y equals the square root of 4 minus x squared, okay? And if we restrict this from x equals 0 to 2, we have a quarter of the circle. So what we want to do, the arc length formula, is we're going to go from 0 to 2 of the square root of 1 plus the derivative of this equation, which ends up being, let's see here, so y equals 4 minus x squared to the half, so y prime is half 4 minus x squared to the negative half times negative 2x, so that is negative x over 4 minus x squared root. So it's going to look like that. So negative x over 4 minus x squared, all squared. Okay, so this becomes from 0 to 2, the square root of 1 plus x squared over 4 minus x squared, because when I square, the root goes away, square the top becomes positive. Okay, and then, well, why don't we just let our calculator handle this? So, doop-a-doo, option, calculator, integral, square root of 1 plus x squared over 4 minus x squared from 0 to 2. Thinking. Math error, did not like that. Where's my error? Actually, we're going to have to longhand it. Okay, so multiply the top and bottom here by 4 minus x squared. So 0 to 2, so 4 minus x squared plus x squared would be 4 over. So we'd have that. I turned the 1 into 4 minus x squared over 4 minus x squared. So 4 minus x squared plus x squared give me just the 4 here. Okay, so then, yeah, because we can't do that. Okay, so we actually rewrite this. Square root of 1 minus 1 over x over 2 squared dx, which is actually, when you do the antiderivative, 2 inverse sine of x over 2 from 0 to 2. So that's 2 inverse sine of 1 minus 2 inverse sine of 0. So the inverse sine of 1 is pi over 2. The inverse sine of 0 is 0. So this would be pi over 2, but that's a quarter of my circle. No, wait, nope, I did that wrong. Inverse sine over... Oh, so I forgot to double it. So there's a 2 out front here. So this is actually just pi. That's a quarter of the circle. So the length of a quarter of a circle is pi. So multiply that by 4. There you get 4 pi. All right, example 10. Find the volume of the solid obtained by revolving the curve about the x-axis. All right. Volumes of revolution. Okay, so our radius, our cross-sectional area is pi r squared. The radius is this equation, so pi times x e to the negative x squared. So what we need to do is, so we're going from 0 to infinity of this equation. Okay. So let's see here. So we can actually factor that pi out because it's just a constant, so I don't need to worry about it. So this is pi 0 to infinity of x squared e to the negative 2x. So let's see, f and g. So we're going to do the tabular method for by parts. So we've got x squared, derivative is 2x, derivative is 2, derivative is 0. E to the negative 2x, so its antiderivative would be negative half e to the negative 2x. Because when that 2 multiplies out front, I need to get this. So then it's going to be positive 1/4 e to the negative 2x, negative 1/8 e to the negative 2x. So let me multiply on the diagonals. So negative half x squared e to the negative 2x, that's that, minus 1/2 x, 2 times a quarter, e to the negative 2x, minus 1/4 e to the negative 2x, all evaluated from 0 to infinity. Okay, so let's see here. And all of this multiplied by pi, because there's still that pi hanging up front. So if I plug infinity in, well, let's do this. Let's rewrite it first. So this is negative x squared over 2e to the negative 2x minus x over 2e to the negative 2x minus 1 over 4e to the negative 2x. So if I double all these, I get a common denominator. So negative 2x squared minus 2x minus 1 all over 4e to the negative 2x from 0 to infinity times pi. Okay, so now let's see what we get here. So if I plug infinity in, can I do that? This is the question. So if I plug infinity in, this whole thing becomes, actually those aren't negative anymore, because now they're on the bottom of the fraction, they're all positive. This is going to grow faster, so this whole thing becomes 0 minus negative 1/4, because if I plug 0 in, goes away, this becomes 4, so negative 1/4. So I have this, which is pi times 1/4, which is pi over 4. So the volume is pi over 4. And that, after all of that, is the end of the section.